Hi, this is Ken Johnson for another episode of SecCast. In this tutorial, we discuss and demonstrate SQL injection. We will briefly show manual and automated techniques before diving into the code that introduced the flaw, explaining and showing the SQL query in action, exploiting the weakness using both manual and automated techniques, and we will discuss prevention. What is SQL injection? Very simply put, it is the unintended manipulation of a database query. This means something an attacker provided to the application allows the attacker to interrupt the normal SQL query and append their own. This is a code flaw, and it shouldn't occur as prevalently as it does. We'll talk about that a little bit later. So we won't go into every string that you could possibly enter here. There are a few sites dedicated to helping with just that, but I want you to be aware of what our input tells us. Here we enter a single quote, one of the most basic tests for SQL injection. Note the error stating that our SQL syntax is broken. This is a fairly good hint. Additionally, it actually shows the query that we are injecting into. This is called error-based SQL injection, and from here you should definitely be able to make something happen. PentestMonkey.net has a fairly decent starter kit for queries you could potentially inject into the application in order to enumerate data and generally have some fun. I'd highly recommend looking for other sites with this sort of information, but we have provided the link to this site in our references section. Additionally, this course is just an introduction. Our company, as well as other companies, have training dedicated solely to this topic. What I'm trying to say is there's a lot to learn about this subject. Now we'll demonstrate a few tools you can use to detect SQL injection vulnerabilities. We'll want to send the authentication request with normal login data to the application and catch it in our proxy before it reaches the web application. We'll right-click on the request and send it to intruder. Once at intruder, we need to clear the insertion points. We only want to test certain parameters. Next, we'll highlight only the username and password fields, right-click on the request, and send it to scanner. I should note this is only available in the professional product. You can see that the scan kicks off right away. It has found something. A quick note, you can always go to your scan queue to see the status of a scan. We'll take a look at the SQL injection finding. As you can see in the first request, the SQL error is blatant. This appears to be confirmed SQL injection. In the second request, you can see that 2 single quotes are used. The reason for this is that 2 single quotes means an empty string was formed, and while the query won't return data, it won't be broken either, so it won't show an error. Remember, this is string concatenation, so if the strings enclosing the data you submit are interrupted or malformed, it will cause an error. In some cases, the error may be caught on the back end and suppressed. This is called blind SQL injection, meaning a SQL injection vulnerability is present, but the error is not necessarily sent back to the client for observation. Next, we'll clear the insertion points and only place an insertion point around the parameter we know to be vulnerable for demonstration purposes. Normally, you'd want to do this with every parameter where applicable. We'll choose a payload, in this case, fuzzing SQL injection, and start the attack. You can see that the results are a mix of 200 and 500 errors. We are really only interested in the 500 internal server errors as well as their corresponding byte lengths, as a 200 response means that nothing really happened from an attack standpoint. Again, this technique would be different in a blind SQL injection test. You can see that 2 separate errors occur. One is an out-of-bounds exception, indicating an operation was performed on an empty array, potentially anyways, and the other is a flat-out SQL error. Both are of interest, but seeing the SQL error means you've detected a SQL injection vulnerability. Next, we use SQL Map for detection. SQL Map is an open-source tool for performing detection and exploitation of SQL injection, whether error-based or blind. So we'll use the -H or help option to look at how to use this tool. We can see that there is a -U or URL option. We will form each of the command line options we need together in a separate file, then copy and paste over the command. We can't easily copy the URL in Intruder, so we'll send the request to Repeater and copy the URL from there. Note that we enclose the URL with double quotes as not to cause parsing errors when running SQL map. We'll use the option -P, and this means we are telling SQL map which parameter to test. In this case, username. Our application has basic authentication as well, so we'll enter those creds. Next, we will run the command. Right away, it appears the backend database has been detected. I'll choose to skip tests for any other databases since I know this is a MySQL database. I'll accept the tests, and after this tool runs for some time, it will notify us that the username parameter is vulnerable. This means we should be able to use SQL map for more than detection. We should be able to use it to exploit the application. The following code is the actual code that we are injecting our own SQL into. You can see that our input, the variables username and password, are concatenated with some hard-coded SQL statements. Adding the variables username and password to the static strings ultimately forms one string of SQL syntax. This string is passed on to the SQL server and then interpreted as well as executed by the SQL server. To give you an idea of what this looks like, I'll pull up a tool called SQL Pro, which allows me to execute queries on a copy of the database similar to the one we are attempting to attack. In a normally formed query, shown here, we can return or grab a username value by saying, if the username equals test and the password equals test, return the username. You can see that there is a username test with a password of test, so this query does succeed and return a username. Now, instead of performing the normal query, let's see what happens if you are able to place your own data inside the SQL query or SQL inject. As an example, we can append or ID equals 1, which says return the username where the username is blank or where their ID is equal to 1, and then comment out the entire rest of the query. The username is still passed back to us. Imagine having the ability to perform SQL queries on a website you didn't own. It provides a lot of power, and this is a favorite vulnerability for a lot of attackers. We will attempt to use the injection string we just tested. Note that we put a single quote in front of our SQL. This is because we are closing the SQL quote that encapsulates the username variable value in order to turn it into an empty string and then run our additional SQL query as normal. The error no longer looks like a SQL syntax problem, but it won't give us access either. Let's look at the code to understand why. We can see the function named login submit, which resides at the URL path of /public/login submit. We take the request from the user and pass it to the isValidCredentials function within our login service. Login service is just a name for the login service impl class. When we take a peek inside the class, we can see this function calls isValidCredentials on our DAO object, which is a name for the login DAO impl class. Essentially, we are taking the username and password and passing it to that function. And finally, we are back at the isValidCredentials with our SQL query, which is string concatenated or injectable. We'll go back to the original login submit function to see what happens after the query executes. We call a method on the login service called populateUserInfo, and we pass it the request. Once again, this calls a method with the same name under the login DAO impl class. Here, you can see that instead of string concatenated SQL, we are using a parameterized request. That SQL, plus the data we provided at the login form for the username, are sent to the SQL query. Then, some operations are performed on the array returned from this query. Unfortunately, this query executes based off the username we provided and not the username returned from the database query, which is injectable. This means in order to return a valid query here, we need to provide an actual username. What I am saying is that while we can inject a SQL query into the username field in the first SQL query we saw, when it gets to this point, we will need a legitimate username and cannot have a SQL query in the username, or else we'll get the array out of bounds exception because we are performing operations on an empty array. Luckily, because the password field is injectable, we can still become a user through manual exploitation of this issue. What we will need to do is find a valid username that already exists on the site. Luckily, this site is vulnerable to this vulnerability at the sign-up page. We enter in some details. Pay attention to the username asmith. The username exists in the database, and when we submit this request, we get an error confirming such. It says that the username already exists. We navigate back to the login form. Let's display the password field so we can see what we're doing. Okay, so once again, we'll enter a single quote followed by a or 1 equals 1. The goal is just to return a true value, since the password we provide won't match up, but it won't matter as long as the statement evaluates to true. The query will return a valid username and allow the rest of the code we've shown to execute normally. We'll navigate to our SQL tool to show how this works in action. You can see it does indeed return a username from the database. This is because even though the password won't match up with asmith's password, we said if the password is equal to X value, or instead if 1 equals 1, return true. I'm not a mathematician, but I'm fairly certain 1 does in fact equal 1, so it makes sense that this would work. Okay, and with that, we were able to inject our own SQL, return a valid query, provide a legitimate username, and allow the code to execute properly. We are now authenticated as asmith. Now that we have thoroughly explained the concept of SQL injection, we'll discuss using automation to exploit it. Once again, we want to use our SQL map tool. This time, we will leverage the --dump--all option, which basically dumps all of the information from the database. I don't mean that it deletes all the data. The data in the database stays intact. This just grabs copies of that data and provides them to you, the attacker. We will go ahead and execute this query. This will take some time to run, so we'll edit this process for brevity. Okay, so the tool ran, and we've gone back through the output to look for valuable information. Here, we can see the user table provided to us. We have a few columns, but we are interested in the username and password. You'll see that there is a role column. This is important in order for us to understand which of these accounts has the most access. You can see that the passwords are stored in plain text. It appears everyone has the same password, strong pass. Now we can authenticate to the application as any user. When discussing SQL injection, you hear the words input validation or sanitize input as the way to correct this problem. Personally, I'm not really certain of how this phenomenon began, but it is inaccurate advice and does not really make sense. It may help prevent against second-order SQL injection attacks, but shouldn't be a method for protecting your queries. The first line of defense is using parameterized queries. A parameterized query means that the SQL query you've written is first sent to the server. Then the server waits for the data, in this case the data provided by the user, before executing the query. At no time does the data provided by a user and the SQL query commingle. So there isn't an opportunity for an attacker to inject their SQL into the SQL query before it is sent to the SQL server, effectively mitigating SQL injection. So let's review one more time our vulnerable SQL query. You can see that the username and password are intertwined within the query. Then the query is sent to the SQL server where it is interpreted and executed. Now let's look at the parameterized query. You can see that the SQL query string is formed. Note the question mark in place of a username variable provided by the user. This is a dead giveaway for our parameterized query. Basically, this is a means of saying we don't know what the username will be, but here's the query we're going to execute. will provide you the data or username value in a follow-up request. On line 86, you can see that we execute query for row set by providing the SQL string as well as a second value, which is the user-provided data. This logically separates the query and the data so that the SQL query isn't modified directly by a user. That's really all it comes down to. Lastly, I want to discuss two other methods of prevention. One is by using an ORM, or Object Relational Mapping Library, to perform SQL queries. When used correctly, and unless there is some obscure vulnerability in these libraries safely abstract a developer from performing raw queries, and much like parameterized queries, separate the SQL query from the data provided by the user. Lastly, it is possible to whitelist data from the user and say that only certain characters are allowed. If second-order SQL injection is potentially something to worry about, in that case, it does make sense to restrict what the user can put into a database, since second-order SQL injection means data is taken from the database and executed as part of some other SQL query. If that other SQL query is vulnerable, this could potentially be a problem. It is really an edge case, and I hesitate to recommend this approach since it could quickly turn into a cat and mouse game of hunting down potentially malicious characters, only to find that you've missed an entire range of malicious characters later. To recap, we've discussed automated and manual approaches to detecting and exploiting SQL injection, as well as defined what this looks like and how it occurs. Lastly, we've discussed some preventative measures to protect an application against this vulnerability. I'm Ken Johnson. This has been another episode of SecCast. Thanks for watching.